This is a video about the dot and cross product. Now we have vectors and we have scalars. So let's say we have a couple of vectors a, b, c, and we have scalars a, b, c. Now when you want to add, you must add vector to vector and scalar to scalar. You can't add a vector to a scalar. However, if you want to multiply, there are various ways you can multiply vectors and scalars. So you can multiply a scalar times a vector, and the answer is a vector that has been changed in length by the factor a. You can multiply two vectors together in two different ways. You can either dot them, in which case the answer is a scalar. So if you do this, it's a vector. Or you can cross them, a cross b, and the answer here is a vector. Now the question is, why do we have these things, scalar and vector quantities, when we multiply using the dot and cross products? Well, there's a couple of different interpretations. There's a mathematical interpretation, there's a geometric interpretation, and then there's the physical interpretation. And I think you guys probably have learned the mathematical interpretation, which you just crank out the answers. But let's talk a little bit about the physical interpretation. Why do we have the dot product in the first place? So imagine that someone comes down from outer space and they've never seen a lawnmower. So they come and then they see this lawnmower. And the lawnmower has three handle positions: position 1, position 2, or position 3. And the question is, in what position do you put the handle to make the lawnmower move across the lawn as fast as possible? To move in this direction, some displacement d. Well, if they've never seen a lawnmower, they really wouldn't know which position to put it in. If they'd never pushed a lawnmower, they wouldn't know. Now, but they do know they can only push so hard. So the force they can apply is fixed, and they do know that the faster it goes, the more distance it's going to cover in a certain amount of time. So what you tell them is, you say, okay, the way you're going to choose the handle position is the speed of the lawnmower depends on the dot product between the force you apply along the handle and the displacement along the lawn. And you want to maximize that. And they'll say, oh, that tells me everything. So this dot product, that simple little expression there, tells them, first of all, it would be completely useless to push perpendicular to the displacement because the dot product of perpendicular vectors is 0. They would also know that if they want to maximize this quantity, they want to have the angle between the displacement and the force vector as small as possible, because mathematically this is equal to the force times the displacement times the cosine of the angle. So they know this position 3, where the force is in this direction and the displacement is in this direction, minimizes the angle, which maximizes the dot product. So that's an example of why we use the dot product. It gives you a tremendous amount of information in a very nice little concise expression. Now, so that's the physical reason. Then there's lots of quantities. How much energy is stored in a compass needle when it swings, how much energy is stored in a dipole in an electric field when it swings. So this succinct way of representing the relationship between two vectors is very handy physically. Now mathematically, if you are going to dot two vectors, you know that you just take the sum of the product of the components. So you take ax, bx, ay, by, az, bz, and you just crank out a number. And whether that number has any physical interpretation, like, for example, kinetic energy, or potential energy electrically, or magnetic potential energy, well, it depends what the two vectors are. That's the mathematics. Now the geometry, if you look at two vectors, A and B, what the geometric interpretation of the dot product is how much the B vector projects onto the A vector. What that means is if you shine a light perpendicular to A, the shadow of B on A, that's called the projection of B onto A. So that's B cos theta. The product of that projection and A is the definition of the dot product. So A, I think I wrote it up there already, A dot B is magnitude of A, magnitude of B, cosine of the angle between them, where this is the projection of the B vector onto A. And you can see that if A and B are perpendicular, clearly the projection is 0. It's also, this interpretation is a way to figure out the angle between two vectors. So if you know the two vectors, you can dot them and get a number. If you know their lengths, you can get their lengths. You can actually calculate the angle between them. So that's a very handy geometric interpretation. Okay, let's go on to the cross product. So now we've got these two vectors. Why do we have the cross product? What's the cross product good for? Well, an example of a cross product would be, imagine someone comes from outer space and there's a door. Now usually I just demonstrate this in the classroom. I'm not very good at drawing a door. So just like the door to the room. So here's the door, and the hinge, goes through here. It's got a doorknob here. And the door is going to be able to swing open and closed. Now let's look down on the door. It's much easier to do this looking down through the axis. Here's the door. So someone comes from outer space, they've never seen a door, and you tell them, go and slam that door, and make it slam as fast as you possibly can. And the force that you can apply is fixed, as much force as you are able to apply. So they go, I wonder how you push the door. Like, do I push, this is the hinge. Should I push over here by the hinge? Should I push this way? And they would have to sort of test it out and try, like, where's the best place to push and what direction should I push in? But you say to them, you don't have to try it out, because the rate at which the door closes is given by a cross product, R cross F, where R is a vector that starts at the hinge and goes along the door. And they go, oh, it's easy. I know exactly how to push. I'm going to push so that, first of all, I make R as big as possible, so I push at the end of the door. And I want to maximize that cross product. I'm going to push perpendicular to R. So I know that the direction I push is this one. And that would give me R cross F, a maximum. And I would even know which way it turns. So if you take R, turn it toward F, the door would rotate that way. And we all know, of course, this is torque. So this is a beautiful way to put a whole bunch of information into a very small, concise mathematical expression. Cross product's a very common thing. So it has to do with torque. This is exactly torque. It explains beautifully why it is that charged particles travel in circular paths when they encounter a magnetic field. It's also related to how dipoles and how magnets swing in electric and magnetic fields, respectively. So that's a physical reason why we have the cross product. Now, mathematically, you guys also know how to crank this out. You do the little determinant with the components of the vectors. Whoopsie. A, and A, B, 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 and you do the determinant of that matrix. I don't have to go through that. You guys know how to do that. Now, geometrically, what does it represent? Now, and also you need to know the right-hand rule, which I think you guys are probably good at, with the fingers and the crossing. That's something else I would have to actually physically demonstrate with my hand. But the geometric interpretation, like what does it mean when you have two vectors, A and B, and you cross them? What does that have to do with this picture? Oh, it's keep going funny on me. Well, what it has to do with, because the magnitude of a cross product is the magnitude of A, magnitude of B, times the sine of the angle between the vectors. So what does that mean? Now, A sine theta is now this vertical distance here. This is A sine theta. And so what that geometrically represents, that cross product, is the area of this parallelogram. Base times height. Base is B, height is A sine theta. So this area is equal to the magnitude, that's the magnitude of A cross B. The direction is perpendicular. So the direction of the cross product is perpendicular to that area. This would be C. If C were equal to A cross B. Oh, no, I got that wrong. You take A, you turn it towards B. The direction that a screwdriver goes is that way. This would be C. Okay. So there it is, the dot and cross product.